In this lecture we will discuss the full bridge inverter circuit, and we will see that how it operates with the inductive load. So you can see the circuit diagram for the full bridge inverter circuit. It basically consists of 4 switches which are shown over here: S1, S2, S3 and S4. So these switches are arranged in this form that 2 switches are there in one arm and the 2 switches are there in the second arm. So there are 2 arms of the switches, and the load is connected between the center point of these 2 arms that you can see. This is point A, this is point B. Point A is the center point of the first arm of the switches, and the point B is the center point of the second arm of the switches. So your load is connected between these 2 points A and B, and you have a DC source that is represented by VDC over here, and I have connected a capacitor in parallel to that DC source. That may or may not be there. It is not an essential part. In some supplies it will be there, in some cases it will not be there. So the generic circuit is basically with only the DC supply. Okay, so I have drawn this circuit 4 times to explain you the different states of this circuit. So now if the current flows from point A to point B, I will consider it the positive current. So I am going to write down it over here. If the current flows from point A towards point B, I will consider it the positive current. And if the current flows from point B to point A, then I will consider it the negative current. And the voltage polarity will be with respect to the supply polarity. Okay, now there are 4 switches, so we can turn them on and off, and we can develop certain output voltage waveform as per our requirement. But there are certain precautions. What is that switch S1 and S2, they cannot be turned on together at same time, because they will short circuit your DC supply. Similarly, your switch S3 and S4 cannot be turned on together, otherwise your supply will be short circuited. So if I say the 1 represents the on state of your switch and 0 represents the off state, so we can write down the equation by Boolean equation for the switches operation. So 0 will be indicating that our switch is in the off state, and 1 will be indicating that our switch will be in the on state. So in this arm S1 and S2, the binary equation will be, Boolean equation will be that S1 plus S2 is equal to 1. It means one switch can be turned on at any instant of time. So I am going to write down that equation, that S1 plus S2, that will be equal to 1. And similarly for the second arm of the switches, I can write S3 plus S4 will be equal to 1. They will be they cannot be turned on together, either one of the switch will be on at any instant of time. And S1 plus S2 is equal to 1 is also indicating that S1 and S2 are operating in the complementary mode. It means when S1 is on, S2 will be off, that will be 0, and when S2 will be on, S1 will be off. So if this is the situation, we say that our switches are operating in the complementary mode, right? So your full bridge inverter may be operated with the complementary mode or may not be. So if it is being operated in the complementary mode, so then it is then these equations will be valid over here. Okay, now let's discuss the operation of the inverter with respect to all possible combination of the switches. So 2 switches S1 and S3 are the high side switches. because in these two switches the positive terminal of the DC source is common, and S2 and S4 are the low side switches because the negative terminal of the source is common between these two switches. So S1 and S3 are the high side switches, and S2 and S4 are the low side switches. Okay, so now if I look at with respect to the high side switches, S1 and S3, so there may be 4 possible combinations which may be there in the circuit, and we can make a table to represent all of those switching states. So if switch S1 and S4 are in the on state, then the path of the current in the circuit will be like that: from your supply through the switch S1 through the load through switch S4, this will return back to the supply. So when the switch S1 and S4 are on, this is the path of the current, and this is the positive current that is going to flow from terminal A towards the terminal B. So the inductive load will store the energy, and the stored energy will be half Li square. There will be a gradually increasing current because of the inductive load. So in this case, the voltage across the load will be equal to the DC supply voltage, and the polarity will be this one: positive at terminal A and the negative at the terminal B. So let's note down in the table. I have indicated these different switching states over here: S1, S2 and S3, S4. So our high side switches are the switch S1 and S3, and the low side switches are switch 2 and switch 4. Okay, so in the first arm our high side switch is on, so S1 is in the on state and S3 is off at that instant of time, and low side switch S2 is in the off state, and the low side switch S4 that is in the on state. So this is our first switching state, and in that case the current is going to flow like that from terminal A towards your terminal B. Okay, so now the voltage across the load in this particular state is equal to plus V DC, and the current is positive, and the switch S1 and S4, they are in the conduction state. They are conducting, and energy in the load is being stored. So your inductor is acting as the load in this case. Now let's suppose that we turn off these switches S1 and S4, both of them are turned off. So your inductor will resist the change in the current. So because of that resistance, the polarity across the inductor voltage will become opposite, because the induced voltage will be negative, and the inductor voltage will be given by L di by dt. The rate of change of current defines what will be the induced voltage across your inductor. So as we are turning off the switches S1 and S4, so we are interrupting the current, so rate of change of current is quite high. So high opposite polarity voltages will be developed across your inductor. So what will happen with this opposite polarity? So you can see the diode D3 will be having the positive voltage at the anode with respect to the cathode, and the diode D2 will be having the negative voltage at its cathode with respect to the anode. So your diode D2 and D3 will be turned on, and the path of the current in your circuit will be like that: through the diode D2 and then through the load, and then through the D2 back to your source, right? So the direction of the current is positive because it is going to flow from terminal A towards terminal B. So this is the direction of the current, but now the current is going to flow from these two switches, diode D2 and D3. So at that instant of time, the energy that was stored in the inductive load, that is being delivered back to your source. So the stored energy that was half Li square is now being delivered back through the diode. So the purpose of the diode in this circuit is to provide path so that the stored energy in the inductor can be delivered back to your source. So in this mode of operation, your inductor is working as the source of energy. So let me call this circuit in mode 1, and let me call it mode 2. In the mode 1, your circuit, your load was absorbing the energy, and in the mode 2 your inductor is delivering the energy back to your source, because you have turned off the switches. S1 and S4 are off, and S3 and S2 may be on or may not be on. So let's suppose that you have applied the pulses to S2 and S3. Will they conduct? No, because these are the unilateral switches and they can conduct only in one direction, and for the time being I am assuming from top to bottom. So because the energy was stored in the load, and if that energy is to be dissipated in the loop, so your S3 should conduct from bottom towards the top, which is not possible, right? Because these are the unilateral switches. These switches are either the BJTs or the MOSFETs or the power BJTs. So all of these are the unilateral switches. They conduct only in one direction. So your switch S3, if you even apply in the second mode of operation the pulses to the gate voltages to the S2 and S3, they will not conduct. The path will be through the diode, right? So there may be the gate pulses for S2 or S3, or may not be there. So the conduction will be through the diode D2 and D3 in this mode of operation, because of the stored energy in the inductor. So now let's look at the table and we write down these switching states over there. So S2 or S3 may be on or may not be on. So if they are not in the on state, so all of the switches, as you can see in this row, all of the switches I have indicated the zeros, all of them are off, but your diode D2 and D3 are conducting. The load voltage is opposite, minus VDC, and the current is positive because it is going to flow from the terminal A towards the terminal B. And let's suppose that if we apply the gate pulses to S3 and S2, but they will not be conducting. Conduction will be through D2 and D3, because the switch S2 and S3 cannot conduct in the opposite direction. So if I write down that state in the table, so I have indicated over here the switch S1 and S4, they are in off state, and the switch S2 and S3 we have applied gate pulses to those one, but they are not conducting. Load voltage is in negative VDC and the current is still positive, moving from terminal A towards terminal B, and diode D2 and D3 are in the conduction state. Okay, now let's come towards the other combination. Let's suppose that we have turned on S3 and S2 as we applied, as we have discussed in the mode 2 operation as well. So if we now look at the, let's suppose that the whole energy that was stored in the inductor, now that has been dissipated in the loop. So that is dissipated across this resistance. That dissipated power will be I square R, and the energy stored was half L I square. The whole of that is either delivered back to your source or is dissipated across the resistance. Now once the whole of the energy is dissipated, now this load will not act as a source, rather it will start absorbing energy now, but the direction of the flow of the current will be like that. Through S3 it will enter into the load, and through S2 it will complete the path towards the source. So this will be the path of the current. Because our switch S3 and S2 are on, we have applied the gate pulses to these switches S2 and S3. So as the gate pulses are applied, they are in the on state, and whole of the energy of the mode 2 has been dissipated. So now the current is building up in the opposite direction. So that is the negative current. As I told you at the start, that the current from B towards A will be considered as the negative current. So the current is now negative and is rising, is building up. So I am indicating it with this. Over here the current was decreasing, right? In the second mode of operation, the current was the decreasing current, and in the first mode of operation, the load current was the increasing current. So now the current is increasing, IL is increasing over here, but that is increasing in the opposite direction, so it is the negative current, right? So now if we turn off S2 and S3 and we turn on S1 and S4, so the current will not flow through S1 and S4, because the current needs to be maintained in the same direction, because there is the inductive load. So if we mark down the voltage polarity of the mode 3, so this point is positive and this point is negative, because this point B is basically connected with the positive terminal of the source. So this point is positive, and the point A is connected with the negative terminal of the source. So point A, you can assume it over here. So the load polarity is opposite with respect to the mode 1, right? So because of now the switching operation, if we turn off S2 and S3 and apply the gate pulses to S1 and S4, so the energy stored in the load will not the current cannot be interrupted. So because of that, the inductor will respond, and this point will become negative and this point will become positive, right? And that can be explained in two ways. So one way is that your inductor is resisting the change, so the induced voltage across the inductor is given by L di by dt, and according to the Lenz's law, the polarity should be opposite with respect to the previous state. So over here it was plus minus in the mode 3, so in mode 4 it should be opposite of that one. And the other way of explaining is that as you have applied gate pulses to S1 and the S4, so this point is now connected with the positive terminal of the source, and this point is connected with the negative terminal of the source. So the load polarity is like that. But the best explanation is the previous one, that is because of the induced voltages across the inductor, the negative polarity will appear. Very high negative voltage will appear over here. That depends upon the rate of change of current, this one. So the diode D4 will come into the conduction state, because the voltage at the cathode of this diode will be high negative with respect to the anode. So diode D4 will be turned on, and because we have the positive voltage over here, so diode D1 will be turned on, high positive voltage with respect to this VDC. So this is only because of the induced voltages across the inductor, right? So we should explain in that way. So because of the interruption of the current that we have made because of turning off the switch S3 and S2, the induced voltages are such that at this point is more positive with respect to the positive voltage level of your DC source at this point. So your diode D1 now is in the on state. So path of the current, if I indicate in the circuit, will be like that. This is through diode D1 back to your source, and over here it will be through the diode D4. So this is the path of the current in this mode of operation, in the fourth mode of operation. So the energy that was stored in the inductor, that is half Li square again in the mode 3, that will be dissipated by giving the current back to your source or to your capacitor that is connected in parallel to the voltage source. So now the energy is being delivered back and the current is decreasing. If you look at the load current, that will be decreasing, right? So finally it will come to the zero, and then this the operation will be repeated again from mode 1. So we have applied pulses to the switches S1 and S4 in the mode 4, but they were not conducting because the current was negative at your load, and S1 and S4 cannot conduct in the opposite direction, so the conduction was through the diode D1 and D4. But once the whole of the energy stored in the load is dissipated in the loop, so then your switch S1 and S4 will start conduction. So that will be that is indicated in this mode 1. So the current will flow through S1, through the load, through S4 back to your source, and this will be repeated continuously. So you will be getting the positive load voltages and the negative load voltages, and the positive current and the negative current at the load. So in the if we indicate the voltages, so in the third mode of operation, the load voltage will be plus VDC, and the positive is at the terminal B. And in the fourth mode of operation, the voltage from A to B will be equal to plus VDC, because your load is connected in parallel to the source. In all of these cases it is connected in parallel to the source, but the terminals A and B are swapped between positive and the negative terminal. So now let's write down the states in the table. Okay, so now looking at the table, I have added a state 0, 1, 1, 0. Switch S1 and S4 are in the off state, and S2 and S3 are in the on state. This is basically our mode 3 over here that we have discussed. So with respect to our mode 1, the voltages are negative and the current is also negative. It is going to flow from the terminal B towards A. So I have indicated in the table, so that you can see over here negative voltage and the negative current, and at that point your switch S2 and S3 are in the on state, they are conducting. Okay, so and in the fourth mode of operation, when we are going to turn on S1 and S4 by applying the gate pulses, but they will not be conducting. The conduction will be through D1 and D4. So that is indicated over here, that we have applied the gate pulse to gate voltage to switch S1 and S4, and S2 and S3, the low side and the high side switches, those are zeros, means they are off. So the load voltage is positive, and the load current is negative, and the diode D1 and D4 are in the conduction state. So let's move over here and briefly look at the voltages and currents. Over here the voltage is positive, the current is positive in this mode of operation, and our switch S1 is on and conducting, and switch S4 is on and conducting, right? In the second mode of operation, our voltage is negative, our current is still positive, right? And the switch S3 and S2, we have applied pulses to those ones, but they are not conducting. Conduction is through the diode D2 and D3, right? They are conducting. And in the third mode of operation, our voltage is negative, our current is also negative, and switches S3 and S2 are on and conducting, right? And in the fourth mode of operation, our voltage is positive, our current is negative, and the switches S1 and S4, they are in the on state, but your diode D1 and D4 are conducting in this mode of operation, right? So this is the summary of what we are getting. So if you look at the polarities of the voltage and current, so in the first mode of operation, your voltage and the current, they are positive, right? So what about your power? Power will be positive. Power is the product of the voltage and the current. So I can say the power will be positive, and the positive power means it is going to flow from your source towards your load. Now if I look at the second part, and if I look at this one, that our voltage is negative, current is positive, so it means the power is negative over here. So what do you mean by the negative power? Negative power means that it is being delivered back to your source. So the energy that was stored in the inductor is now being delivered back to your source. It will be either stored in the capacitor that is connected across your load, and if the current can flow in the reverse direction in the DC source, and it has the storage component, so the energy will be flowing back to your source. Okay, so power is negative in this case. Now if I come towards the third mode of operation, in that if I look at these things, so over here I can say the power will be positive again. Why? Because voltage is negative, current is negative, their product will be positive. So positive power means now the power is going to flow from your source towards your load. So the direction of the current is this one, and that is indicating that your energy is being delivered from your DC source towards your towards your load. And in the fourth mode of operation, if we look at the polarities, the voltage is positive, current is negative, and the switches are on. So this is indicating that the power is negative, so that the energy that was stored, the power is basically being delivered back to your source. The energy that was stored in the inductive load is now being delivered back to your source. So in the mode 1 your power is positive, in the mode 2 your power is negative, in the mode 3 your power is positive, and in the mode 4 your power is negative. So in two modes of operation it absorbs power from your source, and in the two modes of operation the energy that was stored in the inductive load, that is delivered back to your source. Now if we move towards the table, so I can just mark down some important things over here. Those will be used later on. So from with respect to the high side switches, this is the state 1 and 0, because our switch S1 is on and switch S3 is off. So it is usually called the state 1-0 state, and this one is given the name off state, in which all of your switches are off, and this state high side switch is 0, first high side switch, and the second high side switch is on, so it is 0-1 state. And similarly you can give the name to all the switching states. Now we quickly develop the switching table looking at this circuit and defining it with respect to the high side switches. So if switch S1 and S3, I'm going to consider it over here, S1 and S3, if it is and assuming that this circuit is operating in the complementary mode, at S1 plus S2 is equal to 1, and the S3 plus S4 that is equal to 1, it means one of the switch will be on at any instant of time in any arm of the switches. So if I say the switching state S1 is 1 and S3 is 1, it means S2 and S4 will be 0, because they will be in the off state. And if that is the case, as S1 and S3 are on, so what will be the load voltage? The load voltage will be 0, because your load will be short circuited through the S1 and S3. So load voltage will be 0 in this case. So let's make a column with the load voltage. So in when switch S1 is on and S3 is on, so load voltage is 0. Now if we look at the combination 1 0, 1 0 means the switch S1 is in the on state and the switch S3 is in the off state, so it means your switch S4 is basically on. So this point will be positive and this point will be negative because point A is connected with the positive terminal of the source and point B is connected with the negative terminal of the source through the switch S4. So your voltage will be plus VDC and your switch S1 and S4 are basically conducting. Okay, so if I say the state 0 1, so that means switch S1 is in the off state and S3 is in the on state. And if S3 is in the on state, your switch S4 cannot be on, that will be in the off state. So S3 is on, so it means your point B is connected with the positive terminal of the source and point A is connected with the negative terminal of the source, so your load voltage will be minus VDC, and at that time S3 and S2 are basically conducting. Okay, next if I say the switching state 0 0 means both high side switches are off, so it means both low side switches will be in the on state, but your load voltage will be 0 at that because your load is not connected with the DC source. So with respect to the high side switches, we can make this table, and the conduction of the diodes I have already explained you in the previous slides, that how your when your diodes will be conducting. So now let's move towards the waveforms, that how we can draw the current and voltage waveform for this circuit. Before going towards the waveforms, one more thing, that if your current is positive in this switching state 1 0, if your current is positive, then your switch S1 and S4 will be conducting, and if the current is negative, then your diodes will be conducting. Diode 2 and diode 3, they will be conducting for the negative current. And if we look at this state 0 and 1, so if your current is negative, then your switch S3 and S2 will be conducting, and if your current is positive, then your diode 1 and diode 4 will be conducting, right? So the direction of the current determines that which set of the switches is conducting. Either your main switches are conducting, or your diodes are conducting. Now we quickly draw the waveforms. First of all, we draw the gate voltages, base voltages, or the control pulses of your switches. So let's suppose that our switch S1 is turned on, and so you will have to apply the gate voltage. So let me call it VG1, right? The voltage applied at the gate of your switch 1. And in order to complete the loop, as we look at this circuit, S1 and S4 needs to be turned on. So this is the gate pulse or the gate voltage for the switch S1, and similarly for the gate voltage of the fourth switch, those will be same. So we are going to apply this voltage at the gate of our two switches, switch S1 and switch S4. So they are turned on for half of the time period of the output voltage waveform, and for the half of the time period they will remain in the off state. So this time is Ts by 2, half of the time period, and from here till this point it is Ts by 2, and after that they are turned on again, right? So by applying the gate voltage, and then will be turned off, and this will be done periodically. Okay, so when S1 and S4 are in the on state, at that instant of time your S3 and S2 must be in the off state. So if I sketch the gate voltage of those two switches, so the gate voltage will be 0 for the switch 3 and switch 2. So that will be 0 for the time for which your switch 1 and 4 are in the on state, and once switch 1 and 4 are turned off, your switch 3 and switch 2 are turned on by applying the gate voltages. Okay, so the gate voltage for the switch 3 and 2 is indicated by this waveform. So I have indicated that which switch is on at what instant of time. Okay, so when your switch S1 and S4 are on, so your load voltage will be positive. So let's draw the load voltages. So that will be this one, that will be equal to plus VDC, and once you turn off S1 and S4 and turn on S3 and S2, so your load voltage will become minus VDC. So this is the load voltage waveform, the voltage across your load. Okay, so then your switch is turned on again, so again the positive voltage plus VDC, and so on. So this is the periodic waveform, a square waveform is appearing across your load. Now let's quickly sketch the current waveform for your this circuit. So when you have the positive current with the switch S1 and S4 in the off state, so let's draw it like that. So when your switch S1 and S4 are on, so the current will be increasing, positive current and the increasing current. So the current waveform will be like this. So your switch S1 and S4, they are conducting, right? So in this interval of time, switch S1 and S4 are basically conducting. Okay, so once you turn off your switch S1 and S4 and apply the gate voltage to S3 and S2, but they cannot conduct in the opposite direction. So at that instant of time your diodes will be conducting, and which pair of the diode will be conducting if you apply the gate pulse to S3 and S2. Let's look at this circuit. So if S1 and S4 are off, so then your diode 2 and the diode 3 will be conducting. So the current will be decreasing, positive decreasing current. So we can draw it like that, decreasing current, but this is when your diode D3 and D2 they will be in the conduction state. Okay, so the current is going to become 0 then because of the switch 2 and 3 they are in the on state, so current will start flowing through the switch S2 and S3, so they will be conducting. Now the current will be increasing in the opposite direction, so the current may be drawn like this. So over here now your switch from this point till this point, your switch S2 and S3 they are conducting, and once the current becomes maximum and there is the transition in the switching states, your switch S1 and S4 again turns on at this point, so they cannot conduct in the opposite direction, there cannot be the negative current, so your diode D1 and D4 at that instant of time will be conducting, and the current will be approaching towards 0. And once the energy stored in the inductor goes to 0, so then your main switches will start conducting, but before that your diodes will be conducting over here. So D1 and D4 they are in the conduction state over here, and then your switches S1 and S4 will conduct. So the current will be increasing. So over here S1 and S4 are conducting, and so for that I can draw it over here. So the current waveform will be like this for the inductive load. So your diodes will be conducting, your main switches will be conducting. So your current will be varying between some maximum value and some negative maximum value, positive maximum and the negative maximum. So your current is changing like that. So in some portion your main switches are conducting, and in some portion your diodes are conducting. Over here your diodes will be conducting, and over here in the positive part your main switches will be in the conduction mode, and then over here will be the diodes which will be on, and over here will be the switches which will be in the on state. So your diodes and switches are turning on and off to give you the smooth operation of the full bridge inverter circuit. So these are the voltages and the current waveform of your full bridge inverter. In the next lecture we will see that how we can represent them analytically. We will look at the expressions for the voltage and the current, and then we will see certain examples of the full bridge circuit, and we will discuss some other performance and quality parameters of the full bridge inverter. That's all for this lecture. For in this we have, if I conclude that one, we have discussed the detailed operation of the full bridge inverter with the inductive load. In the case of resistive load, the current waveform will be simply the square waveform, just like your voltage waveform, right? So thank you for listening about the full bridge inverter circuit.